and welcome to this lecture on fundamentals of AR, VR, XR systems. In today's lecture, we will cover system architectures, displays, optics and rendering. To start this lecture, I would like to ask you a question. Well, when you move your head while wearing a VR headset, how does the VR virtual world appear to move naturally and instantly? So, think about it. When you move your head in the virtual world, let us say like this, wearing a VR headset, how does the virtual world appear to move naturally and instantly? We will learn about the answer to this question at the end of today's lecture. So, the learning objectives for today's lecture are that you will be able to describe the major components of an XR system. You will be able to explain how displays and optics create immersion. You will understand about stereoscopic rendering. You will be able to describe the rendering pipeline and you will understand why latency is crucial. First, let us understand the anatomy of an XR system. An XR system is more than a headset. It typically has 5 interconnected subsystems. These include forms of input, tracking, processing, rendering and output. So, I repeat, there are 5 interconnected subsystems: input, tracking, processing, rendering and output. So, the input may be typically in the form of some controllers, for instance, which you may hold with your hands. You are constantly being tracked, typically your head motion, your gaze, these are tracked very well by XR systems. Then all of this information is processed, and after the information about your movements are processed, then the render on your display typically changes, and you can see that altered render as output in your display. So, really the immersion emerges from the coordination of all of these 5 subsystems. We can think of XR as a closed feedback loop. In traditional media, you have the user and you have the content, and typically the user can only watch the content. For instance, in television, you can watch the content, okay. But in XR, you can interact with the content, you can interact with the XR system. The system takes your motions, takes your inputs into account and updates itself. So, there is a continuous interaction loop. This does not exist, for instance, when you are watching a series on television or you are watching some football match on television, okay, or you are watching in a movie in a cinema hall. This kind of continuous interaction loop does not happen. So, in traditional media, you are not able to actually influence the content in any way, whereas in XR, you are in a continuous interaction loop such that what you do makes an impact on what happens next within the system. So, system constantly updates according to your head movement, your eye movement, your hand movement and changes in your environment. The typical update frequency in XR is of the order of 60 to 100 times per second, or we can say 60 to 120 hertz. A key question is, well, why do we need to render or make an update in the XR system in a real time basis? So, why does real time matter? So, you can imagine turning your head and seeing the virtual world update 1 second later. Let us say it takes 1 second to update the virtual world. What would happen as a result of this is that you would sense a loss of presence in that world, you would experience some kind of motion sickness possibly, or overall your feeling of how you are using the system will reduce, or you will have reduced usability in the system. And that is why XR requires immediate sensing, requires immediate computation and it requires immediate rendering. So, as a design rule, we need responsiveness in the XR system. responsiveness is more important than how realistic pictorially your display appears. So, it is more important than what we call as photorealism. Our display may not be very photorealistic, but if it renders quickly according to our movements, so we will enjoy and be immersed in the environment, will sense presence in that environment. There are a number of input subsystems that XR systems use. These can include physical controllers, hand tracking, eye tracking, even voice commands and body tracking. An example of physical controllers are the controllers that come with the MetaQuest series of headsets, be it the MetaQuest 2 or the MetaQuest 3 or Pro. These will typically come with two handheld controllers. Many XR systems will track your hands as well, and that leads to a natural interaction between you and the system. So, you may be able to use your hands to make some gestures. For instance, you may be able to pinch and scroll a screen, or you might be able to sort of feel like you are touching and scrolling the screen, or you may be able to click on some buttons. Okay. So, that is possible due to hand tracking. Very often these XR systems will have eye tracking, which will be able to detect how attentive you are and where your attention is focused within the display. You may be able to speak to the XR system. So, be able to give some voice commands, and that will lead to hands free interaction. So, in that case you do not need to give your inputs through your hands, you can just speak. So, some XR systems will also work with voice commands. Equally, you may be able to use full body tracking, and that leads to full body immersion. Now, such systems are limited. There are only a few systems where the full body is tracked, and if your full body is tracked, then your full body gets immersed in that virtual world, not just your visual senses and your auditory senses. The typical processing subsystems in XR include the computational core. Its responsibilities are to carry out simulation of the physics based on your movements. It will help you manage the interaction. The processing systems may also include AI integration or networking. So, for instance, getting on the internet and managing the scenes. So, typical responsibilities of the computational core are physics simulation, interaction management, AI integration, networking and scene management. Typical examples of processing subsystems include the Unity engine, the Unreal engine and OpenXR pipeline. So, these sorts of engines usually are able to simulate the physics, manage the interactions you are having with the XR system, integrate AI as needed, connect to the internet and also manage the scenes. Then there are rendering subsystems which transform your digital models into visual experiences. So, their job is to render the digital models on the screen in an appropriate manner, so that you feel immersed in the world. The typical tasks of such rendering systems include geometry processing, lighting, shading and texture mapping. So, these rendering subsystems process the geometries and have them move. They are also responsible for creating an environment with the appropriate lighting. For instance, indoor lighting as opposed to outdoor lighting, day versus night, different times of the day, all of that is handled by the lighting rendering. The next important aspect of rendering is shading, which is to give different shades to objects. For instance, an object may have different shades due to different angles at which light is falling on them. There might be shadows, for instance, those might need to be shown. Again, rendering systems are responsible for those as well. You may need to show different textures. For instance, grass will be a different texture than water, than the sky, than furniture objects with different levels of furnishing. So, all of these textures need to be mapped and shown accurately in your VR display. The output of these rendering systems are usually synchronized images for the two eyes. So, two synchronized images for the two eyes, because once you put on the headset, there will be usually two lenses and your display will be split into two halves, and so there must be two images which are synchronized on your display, and then your brain fuses them both to show you just one output image. Various output modalities exist in XR. So, XR communicates using visual displays, auditory spatial audio, haptic methods using vibration and force feedback, and increasingly the emerging modalities in forms of thermal displays, olfactory displays, wind simulation, etc. So, there can be various output modalities. You may recollect the sensorama, which we talked about in the earlier lectures in the history of AR VR. Sensorama attempted including various modalities, including for instance wind, smells, your visual display, sound, etc., as early as 1962. Now, the various platforms that have different types of XR displays. For instance, Pokemon Go is an app that uses your smartphone. Your tablets will usually carry a number of educational augmented reality apps. Smart glasses such as HoloLens have their own display methods in which there is a small camera attached to a glass that you wear. Then there are complete head mounted displays as in the Quest or the Apple Vision Pro. Then there are projection systems such as cave systems, which we will see in this lecture. Something for you to think about as we move along this lecture: which display type provides the maximum immersion? Think about it. So, we have seen 5 display types here: smartphones, tablets, smart glasses, HMD and projection. You may want to think about which display type provides the maximum immersion. Head mounted displays are the most common XR platform. So, you may have seen in the trailer video of this course that I had put on Quest 2 head mounted display. So, that is typically your most common XR platform. Its key characteristics are that it is a personal display that is specifically just for you, the person who puts on the headset. It offers you a wide field of view. It usually comes with head tracking, and it usually has stereoscopic viewing. So, 2 lenses which carry 2 synchronized images, and your brain fuses them to show you one image. Now, these sorts of displays come with a number of advantages. They usually offer you high immersion, as once you put on the headset, then you are cut off from the real world and you suddenly move into the world that is being shown on your display. These head mounted displays are typically portable. You can carry them along with you. They will fit easily into your backpack, but they come with a number of challenges. They will usually be somewhat bulky. So, if you put them on for several hours, you will start feeling the weight of them. They are limited by their battery life, as they are not connected to any other exterior power sources. So, eventually their battery drains out. So, after 2, 3, 4 hours, maybe the battery would have drained out, and you will have to recharge it before you can carry on using the XR system. Usually, as you keep on using, there is also heat due to the electronics that are running on the headset. So, there is heat generated, and this heat also affects the functioning of the display system. Let us look at what make up an HMD. These are the components of an HMD. Usually, these HMDs will have foam padding on the outside, then there are the 2 lenses, followed by a housing in which the foam padding and the lenses are packed. There is some jack for the audio, then comes your display on which the images are projected. Behind that, there might be the PCB board, which has a number of sensors on it, and usually there will be a outer cover. So, HMD will have displays, lenses, cameras, potentially some IMU sensors, microphones, processors, and some speakers. The various display technologies that can be used for creating these XR displays. One of them is LCD. LCD displays are usually cheap and they are mature, but of course, they do not offer high degree of contrast. So, it is a very old technology relative to other display technologies. So, it is quite a mature technology, but the contrast offered by them is low. Then there are OLED displays. These usually offer deep blacks and high contrast, but they come with the disadvantage that they may burn in. Then there are micro OLED displays. These offer very high pixel density. They are very good for premium XR and are usually quite expensive. The future technology that is being worked on is micro LED. These are usually bright and quite efficient as well, but the technology is not yet mature. It is important to maintain high resolution and pixel density in your XR systems, because low resolution causes what is known as the screen door effect. So, you may see some visible gaps between the pixels when you use lower resolution. The effects of such low resolution displays are that they offer you reduced realism and they may cause you eye strain. So, modern XR systems will typically target 2K to 4K pixels per eye. Another key concept is that of the refresh rate. This indicates the number of images that are updated per second. Typical refresh rates are 60 Hz, 90 Hz and 120 Hz. Higher refresh rates usually will reduce the blur, improve your comfort and increase the realism that you get from your XR system. Another key concept is that of the field of view. It is the extent of the visible world that is shown on your display. Typically, human vision in the real world can see up to 200 degrees. So, if you think about me, so I can see everything in my line of sight in the V, but also I can see my peripheral vision can see a little bit around me, beyond me as well. So, horizontally I can see around 200 degrees, but head mounted displays will limit you to 90 to 120 degrees. The larger is your field of view, higher is your immersion, but then it requires a lot of computation as well. So, the greater is a computational demand on your headset. Next we come to optics in XR systems. Displays are usually physically very close to your eyes. Now, without optics, users usually cannot focus properly. So, what we need is lenses which can magnify images, expand your field of view and improve your comfort. In earlier VR systems, we typically used Fresnel lenses. These had the advantages that they were lightweight, they were thin and they were cheap, but they came with some disadvantages as well. Usually there was glare in such lenses, you could see some God rays in such lenses which were not realistic. Clarity was not that good with such lenses. So, really you need to think about which lens to use, so that you can overcome these sorts of disadvantages. In newer systems, typically pancake optics are preferred. These are typically packed in smaller headsets and they give you good image quality, distortion is minimal. So, with pancake optics as compared to Fresnel lenses, you will get a smaller headset. But the key challenge with such optics is that the manufacturing process of creating these pancake optics is usually more complex. Pancake optics is used in the Quest 3 and the Apple Vision Pro. Another key concept is that of human depth perception. If we think about how humans perceive depth, the brain is combining multiple cues to give you sense of depth. This includes binocular disparity, the differences observed by the two eyes, motion parallax, which we will study a little bit later. Then there is the perspective view that we get from images, occlusion due to objects in front that tell us which one is in front and which object is at the back, giving you the depth of different objects, and also from shadows. So, from all of these cues, usually your brain is able to tell the depth at which different objects are. Now, XR systems usually attempt to recreate all of these cues, that is binocular disparity, motion parallax, perspective, occlusion and shadows. Let us understand stereoscopic vision once more, which we have talked about in previous lectures. In stereoscopic vision, left eye receives one image, right eye receives another image, the brain fuses them. The result is that you are able to sense depth. This principle was used by the stereoscope, the ViewMaster, and also in modern VR systems, which we have seen earlier. Let us understand motion parallax. When we move, nearby objects move faster than distant objects. That gives us a cue about the depth. So, we can tell which objects are nearby and which objects are distant, depending on how fast they seem to move. Without this kind of motion parallax, virtual worlds will feel flat, and so we need to replicate this in our VR systems. A key effect that can help us understand this is stroboscopic effect, which is a visual phenomena which is caused by aliasing that occurs when continuous rotational or cyclic motion is represented by a series of short or instantaneous samples as opposed to a continuous view at a sampling rate close to the period of the motion. So, here you can see on the right an example of that. If you see here, this clock is seemingly moving continuously. Here you can see the clock appearing and disappearing, and here you can see it is rotating. So, you can see here that the arrow is rotating in a counterclockwise manner. So, this is also known as the wagon wheel effect. So, in video you can see that spoked wheels appear to be turning backwards, as you can see in this image, okay. And that is because of what is known as wagon wheel effect, similar to what you would see on horse drawn wagons. So, when you flip through quickly a sequence of pictures, it will give you the illusion that there is motion, even if it is as low as 2 pictures per second. So, you can see that there is an illusion of motion in both this as well as this. All we are doing is we are flipping through pictures very quickly, and that is giving us an illusion that there is motion. Above 10 pictures per second, the motion even appears to be continuous rather than perceived as individual pictures. So, this term stroboscopic effect was coined by Simon Stamfer in his 1833 patent application, also known as the phenakistoscope. In 1878, there was an attempt to create a video with evenly spaced 24 cameras along a track, and they were triggered by tripwire as the horse passed. You can see the effect of that. So, you can see the image numbers here. It almost appears as if we are seeing a video of a horse running, and that is possible because we had 24 cameras capture the individual scenes, and these pictures were put together frame by frame, one after the other, and that resulted in one of the very early videos, which is known as the horse in motion video. Another key concept is that of the vergence accommodation conflict, which is a challenge in XR. Typically, your eyes will tend to converge at the virtual depth at which the image is formed, but your focus remains fixed on the display. As a result of this difference between where the image is converging and where your eyes are focusing, that is the display, you can experience eye fatigue, visual discomfort, and indeed this problem has not been completely solved. So, this is still an open research problem. So, your typical XR rendering pipeline will consist of a 3D model, which will be processed, lighting will be added to on top of that, and that will be rasterized and shown on a display. So, that is your typical rendering pipeline in XR systems. For processing the geometry, you need to convert the models into forms that can be rendered. Typical tasks include transforming the geometry, scaling the geometry, rotating them, and using perspective projection in showing your geometry. So, these geometry processing developments were the foundation of today's computer graphics, 3D computer graphics. What is also important in XR is lighting and shading. Lighting matters because users need to infer the shape of the objects, material, and at what distance they are. If the lighting is poor, you will immediately see a break in realism. Real time rendering on XR displays comes with a number of challenges. XR demands high resolution, high frame rate, and very low latency. Achieving all three simultaneously, that is a very high resolution display at a high frame rate and with very low latency, is very difficult simultaneously. And this is typically known as your XR performance triangle, that is managing resolution, frame rate, and latency. So, you can think of this as a triangle. If you improve the resolution, maybe the frame rate cannot be that high, it goes down and your latency will be high, whereas we want it to be low. And equally, if we lower the latency, the resolution needs to be low and maybe the frame rate needs to be low as well. So, indeed there is this trade off that needs to be dealt with. Typically, we will go for what is known as foveated rendering, which uses eye tracking, and it shows you high detail at the center of the gaze and reduced detail in your peripheral vision. Foveated rendering reduces the computational effort that is needed and also provides you with higher frame rates. A key parameter that we discussed or talked about was the motion to photon latency. It is a critical measure of how good an XR system is, because it measures a head movement and how much time it takes to update the display based on your head movement. Okay, so, motion to photon latency measures the time that is required to update the head movement on your display. The target is typically less than 20 milliseconds, and the lower the latency is, the higher you will have a sense of presence in your XR system, and the less will be the sickness that you will experience. The number of key challenges in developing the XR applications, these include the use of advanced computer vision techniques, identifying objects, reconstructing shapes and identifying lighting sources in the real world, determining how to draw the virtual objects that appear to be naturally embedded in the display. Vision algorithms also make frequent errors in unforeseen environments, and we need to take care of them. We need to estimate how real world lighting conditions determine how to draw the virtual objects. Any shadows that they might cast onto real parts of the environment and other virtual objects need to be also taken care of. Furthermore, the real and virtual objects may need to be perfectly aligned in some use cases. So, all of these challenges place strong burdens on both tracking and computer vision systems. Now, how do we solve these challenges? Typically, we need a fixed screen which would show images that are enhanced through 3D glasses. A digital projector could augment the environment by shining light onto objects, giving them new colors and textures, or placing text into the real world. We could use a handheld screen which is part of a smartphone or tablet, which could also be used as a window into the augmented or mixed world. There are two types of displays that are commonly used. One is the see-through display, the other is the pass-through display. In a see-through display, users see most of the real world by simply looking through a transparent material, while the virtual objects appear on the display to disrupt part of the view. Achieving high resolution, wide field of view and the ability to block out incoming light, see-through displays continue to be used in many XR systems. In pass-through displays, you send images from an outward facing cameras to a standard screen inside of the headset. But this comes with issues of latency, optical distortion, color distortion and a limited dynamic range. So, both types of displays are used in XR systems and they have various pros and cons. In see-throughs you get high resolution, whereas in pass-throughs there might be latency and there might be optical distortion and color distortion, but still pass-through displays continue to be popular. Let us see an example of a see-through experience. This is a Canon M-Real X1. So, this is a typical see-through experience. So, an example of a use case of the Canon M-Real X1 is shown here. In a car showroom, a person puts on a headset and on top of the world he can see a car has been rendered through his visual display. And is literally able to touch the car and almost feel it in his own space. One can even step inside and get a sense of how to drive the car. as well as the interiors of the car. Another use case shown here is that of the manufacturing industry. Where you can actually move various system components and see the effect of them on a real world system. You can literally see the interiors of an entire machine system. Another use case is that of medical practice, where you can put on the headset to imagine yourself as if you are inside an operating room. You can literally see in augmented reality where a tumor is located in a patient's lungs. Another example shown here is that of a hotel lounge. Here one can experience, for instance, a concert that is taking place inside the hotel, as if there are real world musicians playing around him. So, it is possible to create new human experiences using VR. You can gain experiences through the eyes of robots or other people. You can give people experiences that are impossible in the real world, such as the experience of flying. You can be 2 millimeter tall and look at ants in their face, or you can be 50-meter tall and tower over a city while people scream and run from you. You can analyze the effect of drugs in the body, or you could become your favorite animal, or you could also become a piece of food. Another key development is in the area of brain connected VR. You can see here a headset that has been connected to a person with a number of sensors, and this essentially a brain interface VR headset. So, in this headset, your brain signals are continuously being tracked and they are being used to give you an experience. So, depending on what you think, the objects in the screen will react to your thoughts. So, this particular system monitors your heart rate at stress, while you are also experiencing a virtual world. There are EEG sensors to track your electrical brain activity. There are EMG sensors which track your muscle activity. There are EDA and PPG sensors to track your sweat and heart rate. There are EOD sensors to track your eyes. So, that all in all, by tracking all different physiological data, gives you a more immersive experience than you would experience in a typical VR headset. Your hand movements are continuously tracked, you are able to use gestures. And your thoughts are being continuously processed to affect the virtual world. So, there are a number of efforts that have been made on improving the limitations of early systems. In early systems, the viewpoint is fixed with respect to the picture. If the device is too large, then the user's head also becomes fixed in the world. So, as an alternative, we may use special glasses that select a different image for each eye using polarized light filters. This has led to the popular 3D movies which you view in cinemas, where you use two different colored lenses, creating what is known as an anaglyph effect. We can increase the field of view by using a curved wide field of view, as in the Cinerama example. This gives us a curved display which is similar to the curved large LED displays, light emitting diode displays that are available today. Lastly, let us look at the cave system for virtual reality. This is a schematic of the cave system. Essentially, it is a virtual reality environment consisting of a cube shaped VR room or a room scale area in which the walls, floors and ceilings are projection screens. The user may wear a VR headset and or heads up display and interact through input devices such as wands, joysticks or data gloves. So, you can see here the walls, ceilings and floor. So, the walls, the ceiling, all of them display images. So, you are surrounded by images inside of the room, and this is achieved by using 3D projectors which are projecting the images into the various walls. You enter through this door and you get surrounded by the view all around you, and you lose a feeling of the real world and you are in a new virtual world straight away. You may wear a headset or a heads up display in such a world and interact with input devices such as wands, joysticks and data gloves. So, here is an example of a cave system. You can see how you feel once you are in the virtual world. All of the walls, the ceiling and the roof are filled with the display. So, you are completely immersed in this world. To summarize this lecture, XR systems are integrated sensing, processing, rendering platforms. So, is an integration of sensing, and the sensor data needs to be processed and then converted into a render on your display. The displays and optics determine the visual quality that you get in your XR system. So, you need to think about the design of the displays and the design of the optics to give a good visual quality from your XR system. Stereoscopic vision creates the perception of depth in XR, and typically you will have two lenses rendering two synchronized images. Your rendering must operate in real time, otherwise you will sense loss of presence in the XR system. And what is crucial in XR systems is low latency for giving you a sense of presence and comfort in the XR system. Now, before the next class, I would like you to browse through recent publications in the below journals, conferences and share one article from the last 5 years that excited you the most on the forum. Some of these interesting journals and conferences are IEEE Virtual Reality, IEEE International Conference on Mixed and Augmented Reality or ISMAR, ACM SIGGRAPH Conference, the ACM Symposium on Applied Perception, ACM SIGCHI Conference, IEEE Symposium of 3D User Interfaces, Journal of Vision, Presence, Teleoperators and Virtual Environments. This I thank you for your attention and I look forward to seeing you in the next lecture.